presentation that is related, that are related to geospatial impact evaluation, the book we have been working on. There are total 3 presentations, and each presenter will have almost 20 minutes. And at the end of presentation, we can have question answer session. So our first presenter is Elinor Benami, and she's an assistant professor of agriculture and applied economics at Virginia Tech. Her research focuses on environmental and developmental economics with the expertise in remote sensing and machine learning. She will be presenting the use and misuses of Earth observation data on weather and vegetation.
Thanks for I wanted to share for good choice with a number of other people, including my lovely co-author, Vivek. Also, this is at the University of Arizona. Mike Cecil was at the University of New England, also covering that. Awesome speaker I wanted to start out by locating us in a particular place in the world on a particular day in January of 2010. And we're looking at 6 different Earth observation products that are reporting. Thank you very much. That are reporting daily rainfall. And so the question is, are you looking at 5 millimeters or are you looking at 30 millimeters of rain? And it turns out that's going to depend on the product that you choose. You can also see, so that's on the left-hand side, you see all of the daily observations of rainfall in millimeters. On the right-hand side, you see what your average monthly rainfall is also in millimeters. And again, you can see a difference that's pretty remarkable from 2 to 6 millimeters. So I wanted to frame this all within the context of gridded weather and Earth observation data are increasingly easy to use. And that is a great gift in many ways. They can fill gaps where ground data are sparse or delayed, possibly misaligned, potentially preaching to the choir here. I think we're all familiar with why Earth observation data and weather information and gridded weather is so powerful. They also make certain types of research designs feasible that may not have been possible really well before. The risk is that products that share this same nominal label, so whether that's rainfall, temperature, or beyond, these can be generated in and constructed in a variety of different ways. And so those construction steps can really matter. We see in a number of different cases that they can change the magnitude and sometimes even the sign of what your estimated effects are. So the other framing that I'd like to share with you all is thinking about the construction of gridded weather data and Earth observation data as one that combines a whole bunch of information together. So we have our physical state, we have our observable context, we have some unobservable confounders, and we have this measurement model, but this is measured with error, and this error is not always classical. I think on the right-hand side here, we often, as economists, tend to think about our data generating structure and our data generating process. And we do think about these questions of error, but let's also pay that same type of attention to the variables that we use often as inputs in this process is one of the main themes of this chapter that we are hoping folks will take away. So there's 4 main parts of this presentation. So we'll talk a little bit about weather, so where rain and temperature numbers tend to come from, vegetation, and with a special focus in on NDVI, given its prevalence in a number of different studies presented here and beyond, but importantly also what it does not see. The question of shocks, so how do we define droughts and floods, and also emphasizing that this is a modeling choice, and then what you might want to do when you walk into your office on Monday after a wonderful week here in Rome. Our chapter does go into more detail about a number of other topics. So we talk about other weather and weather adjacent variables, evapotranspiration, soil moisture, wet bulb temperature, vapor pressure deficit, particulate matter, relative humidity, and wind. But these are the main things that we're going to speak about today. I remember when Jeff and I were originally talking about this chapter, there was this question of, oh, well, you know, if it rained in a particular location, this is a measure of objective fact. You have, again, this measurement of millimeters. I also teach a class on remote sensing in the social sciences, and I remember one of my students coming in and saying, oh, well, like I'm looking at this map and here's this quantitative measurement, so it must be true, right? Not necessarily. We first, in our chapter, will talk about 4 different ways in which you can create a gridded weather data set. This is adapted a little bit from the framework that's laid out in the Alfhammer paper from 2013. But the interpretation of this is you go from more observation-driven to more model-driven approaches, where you go from stations, which a lot of people consider to be, in many ways, the gold standard, but that if you look into the documentation of where they actually come from, you'll see that siting is actually rarely random. They tend to be located in places where we have, for example, airports or other economically important locations, places that are affected by conflict. Will also have fewer stations and may have fewer of them as conflict goes on, and places that have complex terrain and that are not accessible to people, not easily maintainable, also tend to not have have systematic under observation, which can really matter if you're looking at, for example, climate and conflict. Satellite-based measures, we can extract information from radiance and reflectance from a number of different sensors. There's some promise here. There's some spatial coherence and consistency in how these are generated. But there's also a variety of different ways in which you might not be able to compare exactly what is coming from your sensors versus what you are extracting from ground-based estimates as well. There's merge data, which then brings together some of these satellites and gauge information. CHIRPS, I think, is a nice example of that. And then we also have reanalysis data. And that's where you have these physics-based models that will take all of this information, often adding in understandings of geophysics and how the atmosphere works, to produce these internally consistent variables. But what we also see is it tends to smooth out some of these extremes. Here's another way of looking at the same question and the same issue that I had noted earlier. Here we have 6 rainfall products, but we also have 6 different distributions. So you're looking at Ethiopia, Niger, Tanzania, Malawi, Nigeria, and Uganda. You see the density here of total seasonal rainfall. But you also see that the mode spreads and tails diverge across these products. So if you're interested in questions of the impact of weather on conflict, or if you're interested in, say, insurance design, or if you're interested in agricultural productivity as a function of weather, then thinking about these differences can be really critical for what you find. And in the Josephson paper that was part of the special issue, they also go into this in greater detail. The estimated rainfall coefficients can vary both in magnitude and sign across products. So the key point to take away from all of this is that the choice of your product is also a choice of a data generating process. You see similar types of issues when you look at land surface temperature. So these are 3 different temperature products for the same area and the same day. And the range goes from roughly 20 degrees Celsius to approximately 26 or 27 degrees Celsius. Again, really important, even if you're just looking at those raw measurements, or if you're trying to convert this into something like growing degree days, for example, where thresholds can really matter. The other thing that we wanted to raise in the discussion of temperature in this chapter is that satellites typically retrieve land surface temperature. Other types of products are often looking at near surface air temperature, and these are not necessarily the same things. They can vary up to, I think what I've seen is like up to 10 degrees, and that relationship can vary with land cover, with elevation, atmospheric conditions, and often tends to be closer at nighttime than daytime. So again, if you're trying to construct variables that are looking at differences between daytime and nighttime temperature, that can be a really important feature to take into account. As many of us have seen in other types of contexts, clear skies can be really important. Satellite-based land surface temperature can have systematic gaps, particularly in environments where you have a lot of cloud cover, so tropical and rainy ones. And this can also be a time period when, for example, temperature and crop interactions can matter, and you want to measure these variables. Overpass timing, again, I think for those of you who work a lot with remotely sensed data and like spend a lot of time digging into the documentation, this is not necessarily clear, but in talking with a lot of, or this is something that you know, but in talking with a number of other economists, it's not always obvious that satellites, well, they observe a particular place at a particular time, and that can also mean that inherently means a particular time of day. So if you're trying to estimate the maximum temperature and minimum temperature, then really looking at what are you getting and when, and how closely does this actually match, again, is a critical piece of how the sausage is made. So that's just a quick snapshot of rainfall and temperature and some of the different questions to be thinking about as you use those. But I also wanted to spend a little bit of time talking about NDVI, which I see in paper after paper after paper and is mentioned very frequently here. And I totally get why. It's something that we're enthusiastic about for a number of different reasons that we'll discuss. It can be really useful, but I also want to encourage us to not use it indiscriminately. And it's also not the only game in town. There's other bits of information that we can extract from a number of different sensors, and we'll speak about that more here. I really like, there's this wonderful hour and 15-minute presentation by Josh Gray, who's at NC State. He's part of the NASA Land Cover Land Use Change team. He did this talk in 2021 about what economists should know about remote sensing. So if some of this stuff is surprising to you and you want it in more detail, he actually has some nice excerpts of looking at land cover maps focused in on Rome in particular. But I'll leave that to you to be a little surprised. But he has this beautiful quote that talks about what satellites actually do. All that satellites do is just tell us how bright the surface is in a particular wavelength region, or what you might hear people talk about as, spectral bands. That is literally the only thing that they do. So if you want to do anything with that, like evaluate land cover or estimate how many leaves there are in a particular place or estimate land surface temperature, then you have to manipulate these data further. So to drive that home a little bit more, what he was talking about in these specific wavelength regions is let's take a moment to think about the physics of how a sensor works, but also the electromagnetic spectrum. So here we're going from about 400 nanometers on the left over to about 1400. There's a much broader range here, but you may be familiar with visible light, maybe Roy G. Biv and your rainbow colors from primary school. But what we want to flag here is when you're thinking about what are the properties of the Earth's surface and how are we extracting information from it, almost every single thing on this planet has different reflectances in these different wavelengths. And so if you want to focus in on vegetation, I think where NDVI comes from and why people are especially excited about it is because it has this particular pattern in the red and the near infrared portions of the electromagnetic spectrum. So red light, plant chlorophyll absorbs red light to support photosynthesis, and then healthy vegetation reflects little of it back to the satellite and your sensors. And the near infrared, so this is part of the light that we cannot necessarily perceive, but a lot of sensors are trained to do. We cannot see the near infrared, but the internal cell structure of leaves reflects it really strongly. So wavelengths that are just beyond the visible, they have often what we interpret to mean a signal of plant vigor. And so in the chapter, you'll also see an example of a variety of different land cover classes that we've extracted from the cropland data layer in the US. And you can see how they match up against all of these different spectral bands. And you can see, yes, depending on the spectral band that you're looking at, some of these classes are more separable than others. So taking these two bits of information about how red and near infrared work together, we can see this construction of these numbers that you keep seeing pop up. Like in Ariel's presentation yesterday, you could see variation up to 0.3, for example. So that tends to correspond approximately with what we see with sparse vegetation, grasslands, early season crops, and lower yielding fields. This is kind of a rough rule of thumb, but there's a couple of other heuristics you can also employ there. Above 0.5, we tend to see more vigorous photosynthetically active vegetation. When you get to something that's near zero or even below zero, because you can go below zero, bare soil, built surfaces, and water. I think sometimes people in casual discussions of what NDVI is, they'll say, oh, this is a measure of greenness, or this is a proxy for yields. But I think it's important to remember first, the casual characterization of greenness is not even in the construction of the index itself. This is some measure of photosynthetic activity. It's not necessarily visible green. And really importantly, and I appreciate some of the papers where people have tried to take yield data where it's available and map it against NDVI, is that its mapping to yield depends on a wide variety of factors. So it can depend on crop type, canopy architecture, the phenology or the seasonal variation that you have. And the other thing that we tend to see is it often saturates above moderate biomass, and that gives rise to all of these other types of vegetation indices that are trying to account for some of the limitations of NDVI. So, as a reviewer, when I've been looking at papers, I do have this question of, oh, excellent. Again, how do we map that correspondence in between NDVI and what's happening on the ground? This point that I made earlier, NDVI can separate some classes better than others, but timing can also really matter. So we see that your ability to distinguish different types of land cover classes can vary depending on the month that you're looking at here. And in some cases, you can see that some crops are very difficult to distinguish from one another in pre-season times, but like during the, as you get closer to harvest, they may become more separable. So crop type masks, the important takeaway here in the spirit of time is that crop type masks are not actually truth. So they are estimates, they are classifications of a gridded area, and you have to put every single grid into some sort of class. So I think that the really powerful example that I think of from Josh Gray's video is he actually shows Rome and how in some places in Rome are classified as agricultural lands because they had to put it somewhere, and it seemed less like all of the other things than agricultural lands. We provide a couple of different examples, and then we talk about some of their construction here. But again, the point here is that crop type masks, like some of these other measures, are these are approximations, they are constructions, and they are not necessarily truth in and of themselves. Where you will also start to run into some issues is particularly in smallholder intercropping environments, also places where you tend to have both more mixed pixels and there's just more stuff that's happening on the ground. And places that have higher cloud cover, which is what's reflected here. This is from a paper that some colleagues and I put together a few years ago, where we were looking at the share of usable Sentinel-2 observations, where in some cases in Western Kenya in particular, you have up to like 50% being usable, which sounds great at first glance, but then you realize a lot of the non-usable observations are in a time period that's really important for crop growth. So this can lead to mistimed phenology, some biases and treatment effects. So something to be on the lookout for. SAR data can help in some cases, but it tends to have a shorter archive, and it's a different way of thinking about and processing information. It's in different types of physics as well. So moving along quickly here, the takeaway from this section is the threshold that you pick really matters. Again, shocks are a modeling decision. We talk about 3 different ways that you can define a shock and extract some examples from the literature about how people define what floods and droughts are in particular as 2 examples. And there's basically 3 main ways that we find folks will define a shock. One is based on an absolute threshold. So whether your temperature is above 40 degrees Celsius or your rainfall is below a certain figure per week or month. You also see in the literature a fair bit of using relative thresholds. So that can be deviations from a local baseline, z-scores, percentiles. These have the advantage of being comparable across space, but these are statistical rather than agronomic extremes. And then we have these agronomic thresholds, which can be really great. So this notion of growing degree days and killing degree days, that's this accumulation of effects over time, but it often also requires some crop and location specific information. And again, like if you're using a particular product and the bias is up to 10 degrees, that can really matter for how you're accounting for growing degree days. And there's some nice examples of how different types of usage of indicators can yield substantially different estimates of, like, again, what we think of as objective fact. And this Sunnison paper was talking about different ways of trying to measure drought in Ethiopia, and again, found this same type of conclusion. We also know that there's a lot of different definitions of what drought can be. And because of that, you have your agronomic, you have your meteorological, hydrological drought, socioecological drought. There's also different ways of measuring this that will capture different ways of accounting for time and the persistence of effects, which in the spirit of time, I'm not going to go into all of these in great detail. They are featured in our paper, but I think one of the big takeaways is thinking about there's not necessarily a single index, and thinking about those persistence effects is one key distinguishing feature among these drought indices. Floods are also somewhat unique because these are more like discrete events that happen in time and place rather than continuous values. And there's a variety of different approaches that people have taken to try and measure floods. There's this Dartmouth Flood Observatory, which has a lot of really great information per event, but has this feature that one of my friends like to call, oh, well,
The author got a little tired, and so he didn't end up including this this event in their archive. It's reporting driven and again, coverage skews to large, visible, and accessible events. You have satellite-based inundation measures, and we also have hydrological models, and in some cases, the blending of some of these different pieces together. But there's some other ways of thinking about floods here too. So again, if you're just using thresholds, when it happens and where it happens can really matter. The same type of inundation can really be ruinous or productive depending on when it happens in the growing season. Also, rain doesn't always translate into floods in this particular location at this time because of hydrologic connectivity. Upstream rain can drive downstream floods up to weeks later. And both these hydrological networks as well as human infrastructure and the degree of adaptation that we have put in place can matter for where we think floods and their impacts will accrue. So what does this all mean for practice? We've posed all sorts of different problems for all of these different issues. We did try and provide some ways of trying to address these points though moving forward, especially because we care about measurement error in this context because it's not just classical measurement error often. It is associated with the ways in which these products were generated, and that can correspond with some of the very same things that we're trying to study in some of these socioeconomic characteristics. So there are some updates to this. I would encourage you not to take this slide to read it too closely, but the main idea is that there are a variety of different errors. There is classical, we are just wrapping out now, so thank you for that. There's classical measurement error, mean reverting error, differential, and then these kind of complex indirect types of error. But the point is understand your data generating process, and that's going to help give you some way of thinking about, should you use methods like multiple imputation? Should we try and link this up with ground data? And how representative is our ground data that maps to the problem we're looking at? There are other types of approaches, looking at quantile regressions, looking at alternative loss measures that map to the construct you're trying to get at. And again, really trying to use thoughtful diagnostics and be transparent about the sources and limitations of the data sets that you're using. So, the takeaways. In the spirit of some of Pontus Olafsson's papers about good and better practices, not best practices, because these are not necessarily universally applicable. It'll depend on the context in which you're operating. There are some things that we would recommend that folks do. First of all is know your data. The number of papers that I have reviewed where it's very clear that they did not read the documentation is hopefully something that this chapter will bring us away from. So read the documentation, look at your distributions, record the product name, version, processing level. That's important. Match your data to your mechanism. Use ground reference information with intent. So I was chastened by one of my geospatial colleagues at some point saying, this is not ground truth. These are all estimates. And it's true, these are estimates of what's happening on the ground. We're all trying to get at this central notion of truth. But your ground reference data in and of itself might also not be representative. So think about this. There's this notion, I think, in the geospatial world of thinking about triple collocation. So think about how all these different pieces of information converge, for example. Which is also testing your products and metrics. It's the fact that it is now easier than ever to use a wide variety of measurements can allow you to really look at where do some of our messages align depending on the product that we choose and where do they start to differ. And in some places, maybe those gaps in and of themselves are an important finding to illustrate, because maybe that is a place where we need to do targeted ground data collection, because none of the previous stuff that we have is going to give us insight into it. And then, of course, the refrain in our field of being transparent, have your processing decisions made explicit, document them, share your code so people can really recover what it is that we're getting and what it is that we're not getting. With the idea here, let's bring the same scrutiny to our inputs as the time that we dedicate and the energy that we dedicate to causal identification, because these are constructed quantities here. So thank you all very much for your time, and I hope you all enjoy the chapter that will be coming out soon. And I'll defer to my colleagues. Thank you.
Thank you, Elinor. So this will be chapter 8 on the table of content. So thank you, Elinor. Our next speaker is Sara Sayedi. She is currently a postdoctoral research fellow at AidData at William & Mary. Her research focuses on land use dynamics, water resources, and environmental risk in data-constrained region. And she will be presenting the third chapter within this book, and that is focused on geospatial analytics and advanced method for impact evaluation.
Hi, everyone. Thank you for being here. I'm really happy to presenting chapter 3, as Kumar said, geospatial analytics and advanced methods for impact evaluation. So before I dive into the chapter, I wanted to just provide some context on where it fits within the book and how it contributes to the broader textbook. So this figure shows, the general workflow that you will go for geospatial impact evaluation. So chapter 2, the chapter before this, Foundations of Geospatial Methods for Impact Evaluation, it walks readers to all of the four first stages, so data acquisition, preprocessing, feature extraction, and spatial integration. And it introduces all of the core concepts and methods that anyone doing GIE is likely to encounter and needs to know. So chapter 3 also covers more or less all of these four stages with a more focus on preprocessing and feature extraction, but it builds on that previous chapter, that foundation, by adding another layer of discussion. It introduces some of the challenges and very specific considerations that are especially important for impact evaluation and that may kind of differ from traditional GIS applications. And it also, the chapter is helping to kind of establish the mindset that readers need to have before they move on to later chapters, which they go into much greater depth on like specific concepts like the chapter we just saw. So it kind of like helps to bring, create that bridge between the foundation like GIS concepts and other specific topics that we need to know for impact evaluation. So that was just kind of like, what is the chapter doing? So why do we even need advanced geospatial analytics for GIS? So the three reasons that is brought in this chapter is that, first of all, interventions, they can have very different effects in different scales. So so in one part of the landscape, an intervention might be very effective. In another part of the landscape, in different conditions, it may not. And also they're very scale dependent. So an intervention might work on a household farm, in a household level or a farm level, but it might not when we zoom out and look at a district or a region, we may not really see the same effectiveness. And also the fact that the environmental and socioeconomic conditions evolve over time. So the interventions that maybe work at some time, maybe not, like when with different conditions will have a different type of effectiveness. And finally, that right now we have access to far more geospatial data than ever before. So, and making sense of all of these new data sets, it can be really challenging. And so these advanced methods will kind of help us to make sense of all of that complexity and extract more meaningful insights for these larger data sets. So as you can see, and we saw in many of the case studies that were presented in any of the GIS that happened, there are many different types of data sets that are used. So they all come in different formats, spatial resolution, temporal coverage, accuracy. And so integrating them are not always really straightforward. And each of these data sets, they come with their own strengths, limitations, and assumptions. And every day we see new data sets are coming out, new satellite imagery. So these can all create an opportunity for us to kind of like create a more richer picture about how the intervention is beneficial. But also it can, if they're not integrated carefully, they can just introduce additional noise like we learned, and eventually maybe even weaken the reliability of our conclusions. And so one of the things that we are trying to look here is like really emphasize to the reader is that the uncertainty that happens within an impact evaluation, it's a little different from the GIS traditional workflow that maybe at each step we can have like sensor error, like uncertainties of cloud masking, and maybe at each step they look minor and harmless, but when all of these add together and we get to the end, like modeling for impact evaluation, they can all accumulate and they can become like very problematic. So with that, I will go to the first stage that we talk about in this chapter. So pre-processing of Earth observation. So all of these more standard steps like radiometric, geometric, or projection and CRS harmonization, these are all very detailed defined in chapter 2, the chapter prior to this. And so like why they're important and like how should they be done. So in this chapter, what we want to kind of talk and push the readers to think about is the more reality of today, that we are now having access to a lot of pre-processed or so-called analyzed ready form data sets. So for example, level 2 Landsat or Sentinel that we can now access through like Google Earth Engine, there are a lot of corrections that are already happened. And so we can have this kind of thought like, oh, these are like ready and we can just like work on them. Now, it's really important for impact evaluation that we look at our very specific questions. So for example, these like general corrections, they work very well with a lot of like land settings or at more general terrains. But for example, if you're looking at water quality as a result of like crop nutrient runoff or something like that, these corrections might not work very well. So these are some of the considerations that we need to have when we're looking using these ready form of analysis. Or if you're looking at a very complex terrain, the geometric corrections might not work as well. Another thing is cloud masking. So for example, here you see the same composite image these are all surface reflectance, so which are kind of labeled as like, these are already corrected. And for Sentinel-2, so each of these have a different kind of cloud masking. And so, for example, when you are turning this to NDVI, all of these different kind of cloud masking can result in a different value of NDVI. And the challenge, I think, right now is that having access to cloud computation, we can now extract, for example, NDVI in a very short amount of time for many large images. And since these values become normalized, they don't really show a very obvious outlier. And if we're not really like carefully like checking them, we may not really be able to detect any error. So like, this is some of the things that we're kind of encouraging the readers to think more carefully and before like using these data sets. So the next concept here is scale, that it is one of the key analytical challenges in this field. So the main idea is that the results can change depending on the spatial scale at which we conduct our analysis. And this matters because interventions, environmental processes, and the available data that we have, they often operate at very different spatial scales. So as a result, we often need to either aggregate fine scale data into larger spatial units or interpret coarse data at finer scales. So when we aggregate data, we gain simplicity and comparability across larger areas, but we also lose local variation. So depending on what the question is, this might be really important once we lose that local variation. So that means that small but meaningful treatment effects can disappear. So for instance, like in field level changes in crop productivity might not be visible if we only look at like this district level averages. And on the other hand, when we try to work with coarse data at finer scales, we can create a false sense of precision. So because we're not really actually adding any new information, we're just redistributing what already existed. So this chapter is also reminding readers that the same intervention can have very different effects depending on the spatial units. And that is really part of the research design. And it's not just like a simple technical check. Another thing that is part of like the data harmonization is that it's introducing the concept of multi-sensor fusion. So it's the fact that not any of the sensors cannot get the complete vision of Earth. So combining these different kind of like optical or SAR data or LiDAR, so all of these together, they can give us a much better picture of what's happening on the ground, but also these come with a lot of complexity and like a lot of considerations when we want to like combine these together. So that is another thing that we go through in this chapter. And so one of the things that I think we see a lot of impact evaluations is interpolation. So like we have a lot of like points values, and when converting them, we want to convert them to continuous surface values to be able to overlay them or like combine them with other of our raster values. We use interpolation methods. Now, these often look very simple and very straightforward in GIS softwares, but in practice, the choice of interpolation method can really significantly change the resulting surface. So it is really important to think what are these point values are and what is the context of the environment. So for example, if we have pollution data, but we also have terrain, so that terrain can really change the continuously of these like values. Or if you have groundwater values, and depending on like where is like the recharge zones, the rivers, or if there are any like major extraction wells, the continuously of these values can differ. So again, it's encouraging readers to have like a great consideration about knowing their data and the environment that is happening. So these are like some of the common interpolation methods that we that are usually used and we introduce. So they each can be more suited for a specific kind of data set, and which we go through like if the data is clustered or like what kind of like outliers they might have. So each of these we go through in the chapter to for the readers to become more familiar. So after pre-processing, we talk about feature extraction. So feature extraction is the step where we transform our raw spatial data into variables that can actually be used in geospatial impact evaluation. So in other words, we are converting that satellite pixels and reflectance values to variables that can be linked to meaningful units that are suitable for analysis. And this is, again, one of those concepts that are really important. And so it is introduced in chapter 2. So like, for example, different spectral indices, zonal statistics, and like more time series. So these are all introduced in detail in chapter 2. But in this chapter, we look at the more kind of more advanced ones. So we're encouraging, those are all like more pixel based. So we are like introducing these new like more advanced methods. So for example, object-based image analysis that especially if we're working in a very heterogeneous landscape where there might be many different land covers, using these instead of treating pixels individually, this approach can group similar pixels into more meaningful objects. So it can really help us for mapping. The next thing is sub-pixel analysis. So for example, here you can see like if we're looking at this river at the edges, so like each pixel, this is a Landsat image. So if we're doing like surface water extent, like we have to assign each of these pixels to either river, water, or riverbed, but in reality, it's really a mix of both. So these kind of techniques will let us to really see what is the percentage of like of the land and the land cover of each of the pixels. And also hyperspectral approaches are introduced in this chapter that we can use many narrow spectral bands to capture more suitable surface and vegetation characteristics. And finally, the chapter emphasized on feature engineering and feature selection. So as we create really more variables, we also introduce redundancy and noise. So the goal is not really to just extract more features, but to extract features that are really meaningful and represent the intervention mechanism and improve our measurements. So so after feature extraction, the chapter goes to introducing just like talking about machine learning and deep learning. So that is like more increasingly central to how GIS are produced, are done. So machine learning is used to directly generate key data sets such as land cover maps or crop classifications. And these outputs can become variables for the GIS. So even if, you know, we're not applying machine learning in our impact evaluation, it's a very good chance that we are using a product that was based on that have used. So for example, the global forest loss data set that are, I think they're used in many studies. So it's important. So we talk about like what are like the pros and cons of these, what are the limitations of these methods, and like for example, that they are highly depending on the quality of the training data set. And so these are things that we talk about, the different, we introduced the different methods of machine learning. So, and which method can be used for what kind of analysis. So for example, with land classification, you can use both random forest and or support vector machines, but depending on like how heterogeneous and what kind of like training classes you have, you might prefer one can work better for another one. Similarly, it goes after we talk about deep learning. And so again, like machine learning, there's a lot of products that we have, like, for example, like the dynamic world land classes or other kind of global data sets. These are all based on methods that were used deep learning. So the key shift here is that instead of relying on manually like design variables like NDVI, slope, or distance-based features, deep learning can learn directly from imagery and extract its own representations of shape, texture, and spatial context. So that makes it particularly useful when we need to identify or map interventions at scale, such as land cover classification, object detection, or infrastructure mapping. So at the same time, the chapter is clear that deep learning is not like a universal replacement for simpler methods. Many times, much more simpler methods might work better, and you know, they are really hard to interpret. So, and again, it goes through different methods for deep learning, and especially so these it shows like what each method can be used for, and also like the predictive ability that these methods can have. So especially if for interventions that we want to see how effective they can be in the future under different climate conditions, demographic conditions that change. These different methods can show us like how effective they will stay in the future. So as these methods become more advanced, they also become more dependent on large-scale data and computing infrastructure. So there is where cloud platforms play an important role. So systems like Google Earth Engine or Microsoft Planetary Computer or major cloud providers such as AWS make it really possible to process this large geospatial data sets efficiently and reproducible across regions and time. So this shifts geospatial impact evaluation maybe away from local processing towards shared computational infrastructure, which directly shapes what can be measured and how consistently results can be reproduced. Now, of course, as the workflow becomes more complex, the focus shifts from just producing results to understanding how those results are generated. So every step in the pipeline, from data selection and pre-processing to feature extraction and modeling, can affect the final variables used in the GIE. So because of that, transparency and documentation become essential so that we can clearly trace how raw spatial data becomes an evaluation outcome. And as models are also becoming more complex, their interpretability becomes increasingly important, which is why this chapter also introduced explainable AI. And overall, like the message is that strong methods alone are not enough, and reliable GIE depends on transparent and well-documented workflows. And at the very end, finally, the chapter we introduce the new generation of Geo AI systems and how the field is evolving and introduces some of the new tools that will be explained in later chapters again. So one direction is foundation models and self-supervised learning, which can learn from massive amounts of satellite data and reduce reliance on labeled data sets for specific tasks. Another direction is like graph neural networks, which are useful for representing connected systems such as rivers, transport networks, and spillover effects across space. And also multimodal approaches combining imagery, climate, and survey data into unified presentations, while digital twins allow us to explore how systems may respond under different scenarios. Thank you.
Thank you, Sara. Our third and last chapter is presented by Vivek Sakhrani. He's a VP of product at Atlas AI, and he's a technologist working at the intersection of artificial intelligence, international development, and civil infrastructure. He will be presenting chapter 10, titled Geospatial Foundation Model for Data Generation and Indicator Production.
Okay, who's interested in the potential of foundation models for geospatial impact evaluation? That's very good. Okay, who thinks it's a crazy idea that this textbook has a chapter on foundation models for geospatial impact evaluation? Everyone thinks it's a great idea. Okay, who has used foundation models for geospatial impact evaluation? Okay, all right. Okay, so let me share a little bit of context on this chapter. 2 GeoField meetings ago in Williamsburg is when we were discussing what else could the textbook benefit from, and I was considering if there was something I could add to the corpus of materials that the collaborators have already submitted. And I'll say that I was very much on the fence about proposing this topic at the time, 15 months ago. I think I'm still on the fence after writing this chapter 15 months later, but let me share why I feel that is. So what I've observed in the last 15 months is that the topic of foundation models has simply exploded in our collective imagination, right? And for many of us, we've tested the capabilities of LLM-based generative models, so ChatGPT, Claude, and more recently Claude Code, for those of us who like to get in there and have the bot code for us these days. So from students' point of view, the students are going to be coming up in an era of methods where they're not coding by hand. They're really relying on foundation models to help them understand how to make sense of these types of model constructs. And the main reason I felt compelled to then actually go through and write the chapter, given the rapid evolution, was because I think it was very important to plant a flag and create sort of that extreme end of the spectrum that could show how a geospatial foundation model could move the needle on impact evaluation. Now, I'm not sure if it would work, so I wanted to try. So in the chapter, let me just talk about the structure of the chapter, and then I'll show you some of the slides. So the way the chapter is structured is it comes after Virginia Zulu's chapter on advanced GeoAI methods. And that's very helpful to have that because it actually addresses a lot of what you covered, Sara, in terms of deep learning models, when to use them, when to fall back on pre-made inference data sets like the land use land cover from Dynamic World and so on. And then Seth Goodman's chapter comes after, and it talks about feature engineering. It talks about how do you automate and productionize pipelines for working with these very rich data sets. So this chapter sort of sits in between and says, if you can fall back on existing methods, perhaps consider using those. If you know what the types of feature engineering capabilities you want to implement are, focus on those aspects because that might be very productive. But then there is a very specific setting and place where geospatial foundation models might make sense. And so this is really setting up the promise and some of the pitfalls of this approach. So GeoFMs, in the context of this book, are addressing the very specific part of the geospatial impact evaluation workflow, which is on the measurement aspect. And so while the goal in impact evaluation is attribution, essentially to answer the very important question of did an intervention have the desired impact while controlling for other possibilities. This chapter is focusing on how do you use a foundation model to generate the data that's going to feed into that impact evaluation framework. And there's two types of ways in which GeoFMs may contribute. So the first one is for feature engineering itself. So how do you produce the features, which are the explanatory factors or the independent variables in your model? And then the second one is, what if you want to predict the outcome variable itself? What if you want to generate that asset wealth index? Could you use a foundation model to do that? And this is all taking place in a context where, as we've all been discussing this week, that the bottleneck could be lack of labels. So data sparse environments, which is very much true of development and impact evaluation settings. It's also a context where, as Elinor has just presented, there's a tremendous amount of uncertainty of a couple of different kinds that we have to contend with. And so could a foundation model help us navigate some of this uncertainty and generate data both on features as well as on the labels itself? And so the GeoFM paradigm is one in which you pump a model, a very large complex model with a lot of imagery and a lot of labels, at least the ones you can get a hold of, and then hope the model does really well at reproducing some of this information, whether it's predicting those features or the outcomes. And this is really designed for data scarce settings. But the reason we think this has a lot of promise is because you could use the same model for a variety of task-specific outcomes. So, for example, the NASA Prithvi model that's trained on a version of Landsat and Sentinel combined can be used for flood mass predictions, so predicting where floods are likely taking place in imagery. It can predict land use and land cover as well, detect burn scars. So it's one model that's been built for a variety of downstream task-specific applications. This also gives researchers a little bit of versatility because you don't know what you might need to predict at a future point in time. So for settings like humanitarian response or for rapid assessments of certain interventions and conditions, these models could play a role. So this is really the promise of why these models exist. But what I've done for the sake of our conversation today is I've actually flipped the order in which this material is presented in the chapters. So I'm actually going to show you the checklist that comes at the end, because I think that's really the most productive part, especially for advanced practitioners and researchers. So the question really here is, what is the additional complexity of geospatial foundation models really buying you as a researcher? If you pick this up and use it, what do you really need to be thinking about and be careful about? So again, just to restate the premise, GeoFMs are very complex to build. They take an exceptional amount of imagery, compute, and labels. You've got to be very careful about how you engineer that process. And so when would this really be productive as an exercise? So the guiding checklist and decision flowchart, especially for beginners who might be interested in this topic, is to say, well, if you have access to physics-based features like the NDVIs, or other types of formula-specific indicators that are coming from the image content of the imagery itself. So what is the spectral intensity telling you, as Gray's video that you flashed up for a second. So if you already know the reading, the measurement that you want to take, perhaps you want to consider using those indices. If that's not available, or if you want to combine that with other features, a pre-produced data set, like someone else's very good land use, land cover that's published and validated, might work as well. But let's say those aren't adequate for the particular purpose. And this is where I think most of us as researchers start falling into, is that either we would want to use someone else's pre-trained model. So this is the suite of models that are available in the S3 suite or other open access models that are produced in the literature with papers and code that could be available. So producing your own land use and land cover or your own asset wealth index for welfare estimation. But as we already know, given the particular types of interventions that we're interested in testing, we might actually need to start building some of our own models, right? And so the most common experience I'm willing to bet in this room is where we have actually started to build some of our own models, download that imagery, set it up in a way that actually works for the context. And this is where most of the conversation at the conference has focused. But when you don't have the ability to do that, because either the model structure is questionable for the particular application, or there just simply aren't enough labels, could you consider using a foundation model? So that's really when you enter into this territory of the promise of foundation models. So again, the checklist is, if you don't have enough labels, if you want to generalize across regions where those labels are not available or where the work may not have been tested before, and where you want to produce a variety of features and potentially some outcome variables at the same time, and you might need to do this very quickly, so you don't have the time frame of a couple of years to work on a PhD paper, for example, right? You might want to do this very quickly for field settings, either for response or for informing investments and policy decision making. So that's really the context here. So the textbook has two tutorial exercises. One of them uses a very recently published foundation model called Almo Earth. It's published by the Allen Institute for AI or AI Square. And this is one of the first foundation models in the last 15 months since I started working on the topic of the chapter to actually release the pre-trained model weights so that you can produce your own embeddings. Now, this has been rare in geospatial because with Prithvi, with Google's Alpha Earth, with Legend's Clay model, none of these models actually ever publish their embeddings. So this is the equivalent of saying, use ChatGPT, pay me $20 a month, have a great time, but I'm not going to tell you about why does the model behave in a particular way. And now for the first time, we can actually test how a Sentinel image or a Landsat image translates into its embeddings and explore that structure. So I thought it would be really fun to publish one of the tutorial exercises where a student could actually pick a location of interest or an area of interest, upload that, and generate embeddings of that location of choice, and then explore what that embedding structure actually reveals about the underlying place on the planet. And Sara, I think you tested some of these models, and it works in about 5 minutes, right? So this is available in a Google Colab notebook now, so you can build your own embeddings for extensive areas if you like. And it addresses and solves a lot of that cloud compute complexity because you can run it in on a CPU or a small GPU, for example. So moving on to, if you were to try that, this is again where you would be positioned in the GIE workflows. So each of the, I think many of the chapters have some version of this workflow presented. So this is my take on that. And so stage 2 and stage 3 is where this Almo Earth embedding space model is now working. So it's a pre-trained model, which means it already has this encoder decoder structure. And when you submit your satellite image to that model, it will produce embedding. So just to give you a little bit more insight into what this embedding structure looks like. Alpha Earth, which released its sort of paper on the embeddings, has about 64 dimensions. So for those of you who use techniques like principal component analysis for dimensionality reduction and some of these statistical techniques, that almost becomes a must in working with these models because you're trying to make sense of how this very high dimensional representation of the Earth is encoding a lot of information. Almo Earth takes that an order of magnitude further. It has 768 embeddings. So one of the tutorials the second tutorial in the chapter actually helps you run the PCA on the embedding structure and then run Euclidean distance-based tests, which is to ask a very simple change detection question of, does this place on the planet look very similar to a nearby place? So for example, if you wanted to detect deforestation or changes in land use, land cover, and the model knows that, and you have the embeddings, and you've got a particular curated set of locations where this is the type of land use and land cover you want to detect, either because of mining, as we heard earlier today, this morning, or other types of industrial activity. A student can now posit that question and has a workflow available in a way that's fully demonstrated from this Ulma Earth embedding structure. So I will actually not cover all of the slides, but I just want to show you some of the behind the scenes of what it's like to actually build one of these foundation models. So again, a foundation model is a very complex neural network that has been shown a lot of imagery and then been asked to do some pretty phenomenal things. In one of the techniques that is used to pre-train these models is called masked autoencoding, MAE. So here's what that very complicated word actually looks like. So we show the model an image, which is on the left. This is an area with fields and some roads and built environment. And I intentionally selected that because it's got a few different land use types. And then we cover up some portion of that image. And this can be randomized and run in very different ways, statistically speaking. And in this particular example, arbitrarily, it's just 60% of that image is hidden. And the model has shown a variety of these images from different settings. And then it's asked to produce the image on the right. So this is quite a phenomenal capability. This is also how human beings recognize pattern recognition for jigsaw puzzles, for example, where you have some sense of what the full picture should look like because of how you've made sense of the world. And even if parts of that picture are hidden, you're able to reconstruct the mental model for yourself. And that's exactly what these models are doing. Let me skip to another type of time-based phenomenon that these models are also starting to get very good at. So when it comes to questions like change detection or interpolation, because you did not have enough scenes for your area of interest, or because many of the spectral, the optical images might be obscured by cloud cover, could you now potentially reproduce the intervening time steps in an arc? So this is another type of smoothing approach, so similar to what you covered, Sara, in your slide, but it's actually the temporal smoothing for a particular place on the planet. And so this is what the temporal smoothing looks like to remove cloud obscuration. So again, on the left, you have in the month of March some bare fields. It's representing what the seasonal profile would look like at that time of the year for a particular location on the planet. You have what that place might look like if you did not have cloud cover. And so you can take an image from a year where you had a good scene, and then a day where you just had an exceptional amount of cloud cover in the same month, so in the month of May. And then in the figure on the right, you have the model regenerating what that place looks like a few months later because it's remembering the temporal profile, right? So it creates a little bit of excitement because now you could perhaps reconstruct gaps in the data, but you also have to start asking a very important question of, if you were to go to that place today, would it actually look like that, right? What if something fundamental has really changed about the structure and the representation of that place? But the fact that the model could do this in a few seconds of submitting a line of code and producing that is again, it's quite phenomenal. So again, going back to the motivation of this chapter, just understanding the raw capability of the physics and the structure and the dynamics of these models. So just one more fun image to leave you with. So this is how these models, the same model, can be run in a format that's using a variety of task-specific heads. So the model is pumped with optical, SAR, thermal, elevation, climate. This is one of your ending slides, Sara. And that embedding structure, the 768 embeddings that are coming from the Ulma Earth model, are fed into task-specific heads. One that recognizes segmentation. So how do you actually identify where fields are located, even in coarse imagery like Sentinel? Second one is a classification, what you talked about, Elinor, where this is a probabilistic assignment of a pixel to a multi-class ontology. And then the regression head. Could you predict asset wealth or welfare in some formulation of your choice? So just to end, again, measurement error is a significant issue. It has, just like every author at the conference has discussed how they address measurement error. You can be assured that all of this measurement error is propagating into foundation models. So this needs to be addressed very specifically. And so there's a section in the chapter that details both the aleatoric uncertainty, which is the noise in the data, but also the epistemic uncertainty, which is, do we know if the model structure makes any sense and is it representative of the type of setting that we're modeling? So anyway, let me end here on a not so positive note. One of the things that concerns me about geospatial foundation models is the ability to be truly generative in nature. So let's say someone shows me an image of the Earth and says that this has all the attributes and the type of metadata of Sentinel. How would I know if it is actually a representation? It's not a noisy representation, but a completely generative representation that is not grounded in reality, right? And so just as it becomes very easy to now use these foundation models for some of the specific research applications, you could try using Gemini from your personal Google account in a browser and have it generate an image of Rome. And it might make some things up, but it will look very, very realistic, right? So that's the thing we're starting to think about in industry is how do we really explain sort of the true distribution of uncertainty behind what these pixels are showing? And are there ways to make that more explainable? And so that's just sort of for the practitioners who are working with the large technology companies, just something to think about. In terms of we are in industry are very good about putting certain things on pedestals because it works in our favor in certain settings. But this is becoming a very important question in the generative landscape. So let me do that.
Thank you, Vivek. Interesting and very important ending. We have to be worried about what we are working with. And now we have almost 10 minutes for question and answer. So please feel free to. And after that, there's a break, so we can continue to keep talking with the presenters and on the topic as well. So. Not that hungry that we are thinking about only food. So this is a good opportunity to ask question before book get published.
So I have been thinking about like geospatial foundation models applications in impact assessment, impact evaluation, whatever. But kind of, I think from a slightly different angle, like I've kind of one application that has come to my mind is like, what if you don't know what the outcome is? And so like you could imagine doing your diff and diff or whatever, where the outcomes are the alpha earth embeddings, and then you just expose, so you see these embeddings changed in this particular way, or maybe you do some sort of kind of like intermittent summarization of like this particular function of the embeddings changed, and then you ex post say, okay, what does that actually represent? Which seems to be a different thing than what you're saying is like the role of, or how you're envisioning kind of geospatial models. I mean, like it seems related in a way, but like, yeah, how do you think about that? Like, is that a bad idea on my end?
Yeah, I could offer a quick reaction and then the others also welcome to come in. So impact evaluation is a structured process that assumes a number of steps. And there's a lot of work that you could do upfront or upstream to even hypothesize what it is you want to measure the impact on or the impact of. And I think this is actually where some of these models are very powerful, because they really help describe and understand as seen through imagery very quickly. So one way to use these models very quickly and efficiently could be to generate hypotheses about the nature of the impact that you might observe in a far off space where you don't have labels on the outcomes. You might not even have a particular outcome of interest, and you want to understand what's worth measuring in that location because it's important for one reason or another.
Billy, and then next you.
Thanks, that was super interesting. I was wondering, like, given all the pitfalls you mentioned, what are the best case scenarios, or what are the best case uses for which we should use these models given their current state? Like, interpolation looked like one option, right? Like anything else, like right now, what would be the easiest thing that I could go and do?
Yeah, so I guess the question is, for what purpose, right? If we do a lot with Earth observation to describe the world and understand how the world is changing, without asking the question, is it changing because of some intervention I created or something I did? So if it's important to understand what's changing and to be able to do that very quickly, even before you set up a research design, these models are great. In fact, that's why Google and LNAI have put these models out. It's because they're very easy to work with in some ways. But going below that surface of understanding what is the true nature, the degree of the change, correlating that with other known or observable factors that you actually may have good data on, I think that becomes a really interesting opportunity for research, actually, where the creativity of researchers could be really powerful. So I think purpose is very important.
Okay, my question was a little bit different. Sorry, I was not very clear. So right now, it looks like if you need to remove the clouds, like this could be like a better option, right? Because I mean, in the past, like people were spending hours telling us how they removed clouds, right? So like those cases, like what are the obvious cases, like for people in your industry, like, yeah, not the meta questions. So yeah.
I have a couple of thoughts related to that, but also maybe another way to flip the question to you is like, what are you using it for now? Might be another way to think about it, but maybe a couple of cases that I've seen recently. So I have a colleague that does a lot of flood detection work up at the University of Wisconsin, and she's had some experiments, basically trying to use simpler models with GFMs and see where they work well, where they don't, relative to the costs of implementation. And one of the things that she's found is like this classic use case of like places where you don't have a lot of labeled information. In those kind of lower territories, GFMs seem to outperform some other types of like transformer-based models that seem to be very popular. But as you get more and more samples, that gain seems to go away. And I've seen that in a couple of different places. If you're looking for additional examples, like in the agriculture space, there's some really great work that's coming out of Arizona State University and Hannah Kerner's lab. Kelsey Dorkson had a really nice set of tutorials that she did recently comparing a whole bunch of GFMs to, and her kind of takeaway was like, because I mean, she works on them and like helps create and design some of them, but she was also like, be very cautious for particularly agricultural applications. A lot of the ones that you had mentioned also have this feature of taking a calendar year of information, which in agricultural contexts is like not necessarily what we want to do. There are some other models out there like Sara that are supposed to give you more. And I think Ulma Earth also has the capability of like defining the windows that you want to be looking at a little bit more. But there's people who are using them for crop type classification as well right now, including the Ulma Earth team. Yeah. And I think some other people who are trying to use them for like specific types of practice detection as well. So I think I would be cautious about for the reasons that you were suggesting in your paper of like trying to use them for cloud removal. Because if you're trying to, remove the cloud so you can get NDVI, but you're creating a whole bunch of stuff based on what you've seen in the past, if you're applying it in the context where you're trying to say, oh, let's like issue payment to people based on their NDVI, then that seems perilous. But maybe some of those cases where you tend to have more limited data and you're running into constraints with some of the other models you're using is what I've seen. But
yeah, I guess one thing I'm trying to explain as a practitioner in industry is that when you publish your research, it's really a coherent process after you've done a lot of work at the end where you've really clarified the narrative and considered a lot of confounding factors. But that's not the doing of the work, right? Sometimes you may want to super resolve a sentinel image just to understand what that place looks like on the ground so that you can understand, like, okay, how do I even set up my research, right? And so in that case, GeoFM might just help you understand, like, how could this place have evolved recently based on what these models know. So it can give you a clue, and that can inform sort of a much more rigorous and structured research design. But just to mention some related papers, also one from some of your collaborators, actually, David Labelle at Stanford on harvesting. The paper's called Harvesting Alpha Earth, so where they use the Alpha Earth model for agricultural applications. So take a look at that. Their findings are mixed in the sense that it works well for some things and doesn't work well for others, but it's worth sort of catching up on this recent literature.
One last question, simply.
Yes, thanks a lot for the presentation. I have some question about how this is going to evolve in two directions. I mean, I would like to imagine what this will look like in 10 years. So do you think that other type of data, such as LiDAR, citizen science, satellite constellation, what is needed actually to improve? Because what you've shown is quite a traditional data models, but I imagine, so you show a scale difference. I mean, you upscale from 70 to 700 dimensions. So this is super impressive, and we can see it works. So what do we need to contribute for that? Do we need to improve other type of data to complement this data? And also one question, when we think about this AI, you have this hallucination. In one of the image, look like the 60% you have the little star. I don't know if it was the hallucinations, and how do we manage that? And will self-correct the hallucination, you think, or will be something we really have to care about? Thanks a lot.
Yeah, so the entire field of computer vision in the last couple of years, like even the last 2 years, has really exploded as a number of researchers are trying to make this work. So the computer vision conference CVPR is taking place in Colorado, and there's a lot of activity. Everyone's asking the same question: is it a better model architecture that addresses some of this noisiness, for example? I would say that if you look at how LLMs have improved a lot in terms of reducing hallucinations to where they're becoming more robust, you'll see similar trends taking place on the vision and Earth observation side as well. And I think about one thing researchers can already do is to control for that is run the same types of bootstrapping or Monte Carlo type models. So you run the same model over and over again to really understand what that distribution of uncertainty looks like. It doesn't answer the question of, like, would the model ever get to a place that it hasn't seen in the historical data, which is partly your point, Elinor. So that I think is a pending question. There's still a lot of work to be done on more agile and more accurate field data collection in a way that can be used by these models. But that is a huge opportunity because these models have been designed for data sparse environments, which means that you don't need as many labels to fine-tune the model. So yet again, we answer the same question of, is Earth observation replacing the need for survey data collection? I would still argue no, but it has changed what you need to collect data on and how much of it do you need and how frequently do you need to do it, right? So there's a lot of promise there as well.
Thank you, everyone. And one last round of applause to our panel.